Hello, I'm Dominic Berry, and today I'll be talking about our latest advances in quantum algorithms for quantum chemistry, where we're applying the tensor hypercontraction method to get the most efficient algorithms yet. The archive number is given here, and this work has just been accepted in PRX Quantum, so it should be appearing soon. The work's in collaboration with people at Google, particularly Ryan Babbush, who's a group leader there. Also, I'd like to thank Joonho Lee, who's an expert in tensor hypercontraction and did the numerics for that. There's also Nathan Wiebe, who is previously at University of Washington, but's now at Toronto. The general motivation for quantum chemistry simulation is that it can be used to design molecules by screening many candidates for particular properties, for applications such as pharmaceutical design, batteries, and fertilizer. Fertilizer is a particular case of interest because it relies on nitrogen fixing, which has a very inefficient industrial process using between 1 and 2% of the world energy supply. Biological nitrogen fixing is far more efficient, but is based on a complicated chemical called FeMoco. It's not been possible to industrialize nitrogen fixing with FeMoco, but the hope is that simulation of it could give the insight needed to discover a new, more efficient industrial process. Given the size of the fertilizer market of 100 billion a year, this could be extremely valuable, as well as reducing world energy consumption by 1% or so. In classical methods, the computation time increases very rapidly as the size of the system is increased, so once you get to something the size of FeMoco, it's intractable, or you need to use approximate methods where it's difficult to know how accurate the results are. We therefore consider this as an important test case to find the complexities of our algorithms. We explicitly lay out the algorithm for this case for the surface code in order to estimate how many physical qubits would be needed and the overall computation time. With our improvements in the efficiency, it would be realistic to simulate FeMoco on early generations of fault-tolerant quantum computers. Our new method gives the best complexity yet for FeMoco, as well as the best scaling for larger systems. This shows the progression of the scaling of the complexities for different algorithms in terms of the number of orbitals n. The chemical system is represented on orbitals, which essentially correspond to a spatial distribution for an electron, and the state for a multi-electron system is represented by each orbital being either occupied by an electron or unoccupied. One can consider a number of orbitals increasing as the system size is increased, which is called the thermodynamic limit, and is the first column here, and was computed for a chain of hydrogen atoms. Alternatively, you can consider the scaling as one system with a fixed volume is represented more accurately with orbitals, called the continuum limit. That's the right column here, which was computed for H4. The first result here is our approach from 2016 with the Taylor series. The complexity for the thermodynamic limit goes as n to the power of 5.3. We estimated that scaling using numerics in this new paper. For our new scaling using THC, we have a power of only 2.1, which is a dramatic improvement. Last year, there was a major advance from the Microsoft group in the paper by von Berg et al., where they double factorized the Hamiltonian, which we estimate gives a power of about 3.4. Our THC results improve on that by more than a factor of n. Our results also provide the best scaling in the case of fixed volume, though the improvement isn't so dramatic. So in summary, what we have found is not only is our algorithm the best yet for the specific example of FeMoco, it has the best scaling, so it can be expected to provide even better performance for simulating larger systems. For these complexities, we're considering the number of non-Clifford gates, which are the gates which are more difficult to perform in an error-corrected quantum computer. Clifford gates, which are things like Hadamard's and C-knots, can be performed fairly easily in the surface code, but other types of gates like T-gates and Toffelees, which are controlled knots, need to be performed by a costly process of distilling special magic states. In early work, the costing was done entirely in terms of T-gates, with Toffele gates implemented with T-gates. However, it turns out that it's possible to distill magic states for Toffelees directly, with the most efficient current scheme being that of Craig and Austin shown here. Moreover, our algorithms typically require Toffelees as the only non-Clifford gates. That means it's useful to just count the number of Toffele gates for the cost. Next, I'll describe the general approach for these types of algorithms. Generally what we want to do is encode the Hamiltonian as a linear combination of unitaries HL. Then the lambda value is the sum of the weights in this linear combination of unitaries. This is an important parameter that governs the complexity, with the complexity scaling linearly in lambda. We construct a step of a quantum walk by using an operation P that would prepare a superposition state with weights that are the square roots of the WL. Then we perform each of the HL unitaries on the target system where the top register controls L. Then we invert the preparation and perform a reflection about 0. Together these operations give an operation W, which is effectively a function of the Hamiltonian in that it has eigenvalues that are functions of the eigenvalues of the Hamiltonian. We can therefore do phase estimation to estimate its eigenvalues and invert the function to estimate the ground state energy. In quantum chemistry, it is typically the ground state energy which is needed because it can be used to determine the size of an energy barrier which governs reaction rates. Now here is the form of the Hamiltonian for these chemical systems. In this standard form of the Hamiltonian, the first sum corresponds to 2 electron interactions and is the most important because it has the most parameters and the largest magnitude. Again, here n is the number of orbitals that the chemical system is represented on, and so this Hamiltonian needs order n to the 4 parameters. The number of parameters needed to represent the Hamiltonian is also extremely important for the complexity. The complexity in terms of non-Clifford or Toffoli gates will scale approximately as the square root of the amount of data multiplied by the lambda value that I explained on the previous slide. A lot of work in this area therefore focuses on finding alternative representations of the Hamiltonian that require fewer parameters. One approach we used before is to take advantage of the sparsity of the Hamiltonian. That is, many of the terms in the Hamiltonian have small weighting and can safely be ignored without significantly affecting the accuracy. When there are fewer terms in the Hamiltonian included, this decreases the amount of data needed, though it is necessary to include the information on the locations of the terms. That's the approach we used to get very good efficiency for FeMoco in our 2019 paper in Quantum. On the other hand, it is unclear what the scaling of the number of terms for larger systems should be. Another approach we used in the same paper that does give a scaling for the number of terms is a factorisation of the 2-electron part. The rank L could be taken to be n squared in order to give the exact Hamiltonian, but it turns out that it's typically possible to take L as order n, which means the total number of parameters is reduced to order n cubed rather than n to the power of 4. We also proposed in that paper to take a second factorisation of the Hamiltonian. That is, for each term in the first factorisation, use a unitary UL to rotate the orbital basis, giving a representation as shown. Then it's possible to again perform a truncation of the rank for each term, reducing the amount of data needed to represent the Hamiltonian. This approach raises a number of challenges, primarily due to the need to perform different unitary rotations for each value of L. These problems were addressed in the new work of von Berg et al., where they showed how to efficiently perform these unitary rotations using a database approach. Another advantage shown in the von Berg paper was that the magnitude in terms of lambda was significantly reduced in this representation. The representation that we consider in our work now is the THC representation, which is shown here. The tensor hypercontraction or THC representation was developed in prior work, for example this reference at the bottom, but our application to quantum algorithms is new. The important parameters in this representation are the chi and zeta matrices. Zeta is the largest matrix and is m by m, where m is a THC truncation and scales as n. That means the number of parameters is massively reduced to order n squared instead of the 4th power or the 3rd power in our single factorisation approach. This reduction in the number of parameters reduces the complexity, but a problem with this representation is that it also increases the magnitude because the value of lambda goes like a 6-fold sum over these parameters, which is significantly larger than for the original form of the Hamiltonian. To get around this problem, we group the terms together like this, so each sum over chi and a can be grouped together into these new annihilation operators C. Here I've shown it as a sum over number operators for these new modes, but these modes are not orthogonal. What we have done is effectively to project the system into a larger basis with larger dimension m instead of n, where the Coulomb operator is diagonal but non-orthogonal. This form is something we derived for this work and is not discussed in any prior chemistry literature we're aware of. Writing the Hamiltonian in this form at first appears to provide a major challenge in implementation. The difficulty is that the rotation between the original orbitals and these non-orthogonal orbitals is non-unitary. We initially considered methods of performing non-unitary rotations of orbitals, but that introduced a whole host of problems and made the complexity blow up. Then I had a new insight that massively reduced the complexity. This is that the Hamiltonian is being encoded in a superposition in our linear combination of unitaries approach. We have a control register that selects the mu or nu in the linear combination of unitaries, and so for each part in our superposition, we only need to deal with one out of our set of non-orthogonal orbitals. This means we can perform a rotation just for that particular orbital, disregarding all the other non-orthogonal orbitals, and it doesn't matter that they're non-orthogonal. That means that, surprisingly, this problem of the non-orthogonality of the orbitals, which at first appeared to be a showstopper, ends up being a non-issue. We can implement the algorithm in a way that's completely unaffected by the non-orthogonality. We can implement the basis rotations in a very similar way as done in the von Berg paper for the double factorisation. In fact, it's also possible to lift the requirement of orthogonality in that work as well, which could potentially provide further improvements in efficiency. The purpose of writing the THC representation in this way is to reduce the value of lambda, which was increased in the original form. Now the value of lambda is given by a much simpler twofold sum, where there can be a lot of cancellation within the individual terms, massively reducing it below what it was before. In the case of FeMoco, we find that the value of lambda is similar to what it was for the von Berg double factorisation approach, and in that approach the low value of lambda was put forward as the main advantage. In fact, when we consider scaling to larger systems, there is better scaling for the THC approach than the double factorisation approach. We performed the calculations of the lambda value of chains of hydrogen atoms and found that the scaling for THC was as n to the power of 1.11 versus 1.88 for double factorisation, with a similar constant factor. If you look at the continuum limit with more orbitals for the same volume, the indication is that the scaling is slightly better for THC, though the constant factor here is worse than for double factorisation. Next, I'll talk about how to actually implement the block encoding of the Hamiltonian. To do this, we need to write the Hamiltonian in terms of unitaries instead of number operators. To do that, we can use the Majorana representation. First, the representation in terms of qubits is to use one qubit for each orbital and take it to be 0 if there's no electron in that orbital and 1 if there is. Then the fermionic annihilation and creation operators can be recombined into the Majorana operators, which are unitary. Using the Jordan-Wigner transform, we can write these in terms of strings of Pauli matrices. Then when we look at the representation of the number operator, they are just identity minus z on 2. Then the intrinsically two-body term in the Hamiltonian looks like this, where we've picked up an additional factor of 1/4 from the 1/2 in the representation of the number operator. That further reduces lambda. There will also be one-body terms coming from the identities here, which will be combined with the one electron part of the Hamiltonian. Next, in order to actually perform this linear combination of unitaries, we will need to perform the basis rotations u nu and u mu. These will be controlled on registers with mu and nu in a state that we prepare, and for each of these we can express them as a sequence of n simpler 2-qubit rotations called Givens rotations. This is a nice simplification because normally we would need order n squared Givens rotations to transform the basis, but here we only need to rotate the basis to orbital 1 in the correct way, which means it can be simpler. This shows the complete circuit for the controlled unitary part of the walk. To perform the controlled rotations, we use the method from the von Berg paper from the Microsoft group. We use a quantum ROM or QROM with mu or nu as input and output the angles needed for each of the Givens rotations for each value of mu. We improve the efficiency by implementing the one-body and two-body terms together. The implementation of the one-body terms is indicated by the dotted rectangle, whereas the entire thing gives you the two-body terms. A further subtlety is that this procedure needs to be self-inverse for our phase estimation procedure to work. The way the QROM works is as shown in this diagram. The idea is that for each computational basis state on the register, some classically chosen data is output. That could be performed by using multiply controlled Toffelees with control on 0, then on 1 and 2 and so forth, with C0s used for each to output the data. When expressing sequential multiply controlled Toffelees in terms of Toffelees, it's possible to cancel most of the Toffelees in between. The resulting Toffele complexity is then no more than the total number of alternative sets of data to output. That's very efficient here because the number of sets of data is only m, which is a set of rotations for each value of mu or nu. In the diagram here, the left and right elbow joints are corresponding to Toffelees. An advantage is that if the target ancilla is known to be 0 after the Toffele, this can be done with measurements and Cliffords, so the right elbows have 0 non-Clifford cost. After outputting this data with the QROM, we perform the n-Givens rotations in a controlled way, using the angles output by the QROM as the control. Then we perform the Z on a single qubit, reverse the rotations, and erase the QROM. As a result of this, we have performed the controlled operations needed in our linear combination of unitaries. The other crucial part of the block encoding is the state preparation. For that part, we used a method we introduced in prior work, which we call coherent alias sampling. The general principle is that for the purpose of a linear combination of unitaries, the prepared state is allowed to be entangled with an ancilla. Because of this, it's possible to use a coherent version of alias sampling to achieve the state preparation. The idea is to initially prepare an equal superposition, then use QROM to output alternate values of L and keep probabilities. We use an inequality test between keep and another register in an equal superposition, then controlled on the result of that, we swap L and the alternate value of L. For this state preparation, we need to output far more data sets than for the rotations, but we can use a more advanced version of QROM. In this version of QROM, the register is separated into lower and higher bits. For the higher bits, we use the original QROM to output data for every possibility for the lower bits. Then you use the lower bits to control swapping the required data into the output registers. When you're using this method, the complexity goes like the square root of the total number of bits of data. This is useful in the case of the state preparation, where there are many items of data with a small number of bits each, but not for outputting the rotations, where there are a small number of items but each has a large amount of data. This advanced version of QROM is why we say that the overall scaling of the complexity goes like the square root of the amount of data times the lambda value. Because of this complexity, we should try to limit the amount of data needed, which can be achieved by giving the rotations and state coefficients to limited precision. We therefore need to choose the minimum number of bits such that the Hamiltonian is still approximated sufficiently accurately. To address this, what we did was to compute the Hamiltonian with these approximations and compare it to the exact Hamiltonian. The idea is to perform a classical computation to estimate the energies and look at the difference between the results for the two Hamiltonians. We did this for two different types of orbitals. The first is the set of orbitals used in the Raya paper. Later work has said that there are some problems with these orbitals. There's a different set of orbitals proposed by a group in Caltech by Lee et al., which is larger but is argued to be significantly more accurate. We give the results for both in order to compare to the Microsoft work, which is focused on the Raya orbitals. The results shown here are only showing how the accuracy changes with the THC truncation order m rather than the truncations of the numbers of bits as well. The red dashed line is the classical result for the exact Hamiltonian, and the black dashed lines show the region of precision that's aimed for in quantum chemistry. So you can see that once m reaches about 350, there's enough precision in the simulation. Here are the resulting complexities we found for the two types of orbitals for FeMoco. We allowed 1 millihartree for the allowable error in the phase estimation and 0.6 millihartree for the estimated error in the Hamiltonian, for a total of 1.6, which is chemical accuracy. This shows the parameters we found to give that precision within 0.6, and we found that complexity of the Rye orbitals was reduced to about 5 billion Toffolies. This is an extraordinary improvement if you compare it to work from about 4 years ago, because the complexity is about a factor of 10,000 times lower. For the Lee orbitals, the complexity is significantly larger at 32 billion, which is mainly because the value of lambda turns out to be larger. We also performed a comparison between the THC method and previous methods, where we recomputed the complexity using the same parameters as we used here in order to give a fair comparison. We found that in every case THC gave the lowest complexity, with about a factor of 2 reduction over the double factorisation approach of von Berg, which was otherwise the most efficient. We actually found that for the Lee orbitals, our previous method of using sparsity even beat the von Berg method, with only 44 billion Toffolies needed versus 64 for the von Berg method. To find the scaling for the complexity for larger systems, we need to use the scaling of the amount of data used in the Hamiltonian. Like I said before, the scaling goes like the square root of that times the lambda value, and I discussed the lambda scaling earlier. Now the THC cutoff m is of order n, so the matrix size m squared becomes order n squared. The number of bits is logarithmic, so the square root of the data is order n up to logarithmic factors. In the double factorisation von Berg approach, there's not a good theoretical reason to expect a particular scaling for the number of terms, though there is an upper limit of order n cubed. It turns out numerically that it matches that upper bound, so we can take the square root of the data as order n to the 1.5 up to logarithmic factors, which is worse than for THC by a factor of root n. We can multiply these factors for the square root of the data by the lambda scalings that we found before to get the overall scaling for the complexity. For the thermodynamic limit of large systems, we therefore get a power of about 2.1 versus 3.4 for the double factorisation approach, an improvement by more than a factor of n. We used similar methods for the other algorithms to give the scalings in this table. We can also look at the complexity in terms of the number of qubits needed against the number of Toffolies. This figure has time going from left to right, with the vertical axis indicating the number of qubits used and the horizontal axis indicating the numbers of Toffolies. This is a useful way to see what parts of the algorithms are the most costly and are potentially a bottleneck. This figure is for a single step of the quantum walk and for the case of the Rye orbitals for FeMoco. Here we can see that the initial QROM is requiring a lot of qubits compared to everything else, and that's what's pushing the qubit cost over 2000. It's therefore useful to make changes to reduce this bottleneck. Here we've made some adjustments that reduce the number of qubits needed to under 700. It's possible to adjust the advanced QROM so it outputs a smaller amount of data with only a modest increase in the Toffoli cost. Here we also output the rotation angles in multiple stages, so we don't need to store them all at once. When we worked out a layout of the quantum algorithm in physical qubits in the surface code, we estimated the whole algorithm could be done on 4 million qubits in under 4 days, provided the physical error rate was 0.1%. With a more optimistic estimate of the error rate of 0.01%, which is very low, the number of qubits needed would be reduced to only 1 million, and the runtime would be reduced to about 1.5 days. To conclude, what we've found is that using THC, we get the highest efficiency yet, where the efficiency is high because we've reduced the lambda value of the Hamiltonian, at the same time as reducing the amount of data needed to represent the Hamiltonian. The projected scaling for larger systems is around n squared, which is more than a factor of n better than the best prior work. For the particular example of FeMoco, we can get the complexity down to about 5 billion Toffolies in the case of Ryer orbitals. I'll just finish by pointing out the archive version of this paper here, and thanks for listening.